Okay, everybody, how are you today? I see I'm covered up by some kind of background. Let me try to get rid of that. Ah, there we go. Hi there. I see Kat, I guess. Hi, chat. Hello. Good to see you. Hope you're enjoying Global Hack Week. How was that stream with Kari, huh? That was a great stream. I was able to catch a little bit of that. Were any of you? Yeah, Kari took us through building an AI personal project, which is great, covering some of this very same topics that we're going to cover in this lesson. Hi there, Manoj. Good to see you. Yeah, looks like we've got a quorum here. So today we're actually going to be talking about something a little bit related, another machine learning topic. Of course, this is AI ML week. Image classification with vision transformers. And you may have seen this workshop a few months ago, but actually it's been tweaked and updated a little bit so that it flows a little bit better and has a little bit better workflow. So hopefully you all enjoy it, and please let me know what you think. So anyway, let's talk a little bit about what we're going to discover today. We're going to implement a vision transformer from scratch. We're going to talk a little bit about theoretical concepts that exist behind vision transformers. You know, what even are these things? We're going to get into it. And even then talks about some practical coding exercises. And yeah, the goal is really to understand VIT, and we're going to implement it using the CIFAR 10 data set. So hopefully you're familiar with this data set, but if not, we're going to cover it. We're going to cover all things Vision Transformer today. So, and Tishan says, in case we missed a hack, where can we access it later? That's a great question. So it should be available as a recording on Twitch TV or YouTube. I've noticed for whatever reason on my machine, it's not showing up on Twitch. Did anybody else have that issue, or is that just me? Looks like Abhinav says, yes, you can watch later on YouTube. Okay, yeah, definitely check YouTube. I'll even send a link to YouTube of our streams, because for whatever reason, the Twitch recordings have not been showing up on my end. Yeah, Abhinav says the same thing. Strange. I'm not sure why, but Doodle Games asked, what the heck is a vision transformer? So we're going to get into that today. But first, we have to check in. This is super important. So I'm actually going to send the check-in link in the chat for all of you to see. And I'm going to send the final solution code. And you're welcome to click into that, but please, please don't look at it yet in detail, because I don't want us all to get ahead of each other. And we're not going to use it yet. But you know, if you are feeling like this is a little too simple for you, then definitely go to the end where we're going to have some challenges. And so just fast forward to the end of this stream, and we'll have some challenges for you to do that we're going to do in the second half of the workshop. Okay, so yeah, definitely check in using the link, and yeah, we love to see who's checking in to make sure that these workshops are relevant to you and that you're enjoying the content. So now to get to Doodle Games' question, what is a vision transformer? That's the next section of our presentation. So basically, vision transformers, or VIT, you'll sometimes hear them called, were introduced by the Google Brain team in 2020. So you can see the post here. I'll even go there. I'll send that in the link in the chat, and even go to visit that website, because I think they have some great presentation about it. So you're welcome to check that out yourself. But, let's see. Having some trouble getting that. Let's see. Oh, there it is. Yeah, so hopefully you can see now vision transformers at scale. And the whole idea was to be able to recognize images in the same way that you could recognize sentences. So they presented this research in 2020, and they're able to get a really good accuracy. And this plot here, let me just show you, shows pre-training compute, which means how much computer resources will you use to train the model. And this is a logarithmic scale, so every new tick is actually an order of magnitude larger. And then you will get the accuracy going up, but always vision transformers beating ResNet in this, which is a more conventional CNN algorithm. So you can see that the potential is there. If you're using CNNs and you are trying to get an improvement over that, check out transformers. Okay. And someone asks, Apollo, where can we get the slides? No problem. I'll send those right along. So here's the slides, and feel free to follow along there as well. And so Avinav says, what is a transformer? Still not sure about that. So that's the next thing we'll talk about. It's something that is used in natural language processing. So have you ever heard of ChatGPT? GPT is a transformer. That's what the T stands for. And BERT was another model that is still used, but more for Google side. And they might use that type of model for some application to translation or some other natural language reading documents. So yeah, it's great. And yeah, ChatGPT is my best friend too. I love ChatGPT. And let's look up what does it stand for. It stands for Generative Pre-trained Transformer. So just looking that up, you can see, right? There you go, transformer. All right, so now just to get into what is a transformer, how has it revolutionized natural language processing? This is kind of a tangent, but very related to what we're talking about. It revolutionized through what's called self-attention. So it allows the model to weight different parts, the importance of different parts of an input sequence independently. So it will process all elements of a sequence simultaneously. That's different than RNNs, which will process the sequence in order. And so every element of the text is able to be weighted according to every other element. Okay, and so it's a very complicated matrix, a lot of mathematical operations going on behind the scenes. But let's talk about the components of a transformer. First, you have self-attention, which enables the model to focus on relevant parts of the input. So in a sentence, you might think the word the, for example, is very irrelevant to the next word in most cases, because it doesn't really tell you much other than you probably will have a noun after the. So that could be one, of, on, prepositions like that. They will have a different structure than, let's say, enables. Enables has a really lot of meaning for the sentence. So you could have different weights for these different words. And then positional encoding is a really important part of transformers because it adds information about the order of the input elements. So which one comes first, second, third, fourth? That's super important for a sentence because you can't switch the words in a sentence however you want them to be. Some languages, it's easier than others, but almost every language has some convention for which words should come first and which should come second. Like, for example, subject, verb, object in English, except for Yoda. Yes. says, except Yoda. That's absolutely true. I love Yoda, though. And somehow we all still understand him, right? But yeah, so that's positional encoding. And then finally, there's a feed forward function. So this is always the case with a neural network. You will always have some sort of forward action where you're going to take these weights and somehow combine them, process them, so that you have some final output, okay? So we'll talk about the feed forward neural network component a little bit today, but we'll get into that a little bit. Yeah, do or do not. There is no try. That's exactly right. And that's how we're going to approach our vision transformers. We're going to implement them. There is no trying. This is only succeeding for all of you. So yeah, now let's talk about extending transformers to vision. So we talked about how transformers would be useful in a sentence. And of course, that's the case. But how could you take a sentence and somehow use the same ideas for an image? It's kind of tricky, right? It's not immediately obvious. So what the authors of this research did, the authors of the Vision Transformer algorithm, they took the image and broke that down into patches, okay? So think of each patch as a different word in a sentence. So for example, you might have patch number 8 here, okay? That's part of the grass on the bottom of the image. And so that might come after image number 3, which is part of the sky, right? So over time, the algorithm can learn the position of each of these patches to realize that the sky usually happens in patches 1, 2, and 3, and then the grass happens in patches 7, 8, 9, right? Similar to how we have subjects at the beginning of the sentence and objects at the end. So hopefully that helps you understand how we're going to think about extending the transformer architecture to work with images. And so, yeah, someone says I've left something. Have I left something? Nope. We're just still talking about vision transformers. And actually, let me just send one more time a link to the slides, because the slides actually, it was a great suggestion, whoever gave the suggestion to send the slides, because it has not only the information about today, but also a check-in link, a link to the code, and basically everything we are going to do today. So that was a great idea. Okay, and one thing I'll say is don't look at the slides, don't look at the solutions to the quizzes ahead of time, because we don't want that. The whole point of the quiz is to test your understanding. But I want you to now answer this question. Feel free to chat it in the chat. And if you're still thinking, don't look at the chat. I'll give you a couple minutes. What is the original domain of the transformer model? Why don't you try to look at these different options based on what we've talked about today? Okay. So just giving you a minute to think about this. So we did mention 2 applications so far. We mentioned sentences and we mentioned images. But if you recall, the original success of the transformer model was in B, natural language processing. So good job to anyone who said B and also A, because A would be the next domain of transformer model, second domain. So nice. All right. And yeah, someone says excited to learn. Awesome. I'm glad some folks are excited about this. So, all right, we're going to do another question now. What is the primary function of the self-attention mechanism in transformers? Remember, self-attention is one of the key components of transformers, and it's really going to define the architecture. So it's super important to understand self-attention. Part of this is actually in the name itself. Self-attention. Okay, we have a few answers, so let's go ahead and go to the next slide. It's B, to focus on different parts of the input sequence. So A, to reduce the size of the model, I guess you might try some kind of dimension reduction or some other mechanism for that, but self-attention will actually really increase the size of the model because you're looking to connect every single patch with every other patch. And we'll see a diagram of how that happens later in the slides. But yeah, then B would be the answer, to focus on different parts of the input sequence so that you want to weight different patches differently. Like for example, if we go back to our castle example, which patches are most important for telling whether an image is a castle? Probably not the sky and the grass, right? It's probably in images 4, 5, and 6 where you really understand these architectural features. So we want that to come through. And as far as speeding up training, that's similar to reduce the size of the model. It's not really a function. But then improving data augmentation, we're actually going to talk about data augmentation. Tishan says, what does data augmentation mean? Don't worry, we're going to cover that today. But let's just leave that question until the end. In general, it means that you are using your data in the most creative way possible to get as many what they call degrees of freedom as possible in your data set. So we will talk more about that. But here's that graph I promised you, understanding transformers. Look at this. Self-attention mechanism, look how complicated this can be to create a network here. You have just one simple sentence. The animal didn't cross the street because it was too tired, okay? But look, it has a relationship to every single word in the sentence. And the more attention is given to different words, like the words coming after it would have a very big relationship to it. And then words that are further away might have a lower level of attention. Okay, but it's not exactly linear. You have to actually connect every word to every other word to get the context. Okay, so hopefully that helps you. Yes, this is a better explanation. Thank you, Green Pie. So just check that if you want to check the data augmentation. And don't worry, we're going to actually talk more about it in this workshop. But yeah, so attention score between any two elements is calculated based on their compatibility. So how related are these two words within the context of the sentence? Right. So another part of transformers, which is really key, is understanding the encoder structure. Okay. So encoders and decoders are going to be the next layer after we do our linear projection of the flattened patches and embed that into our training input. Oh, sorry, I guess I didn't really talk more about that. But this is a little bit complicated, so I don't want to get too far into the weeds with it. But essentially, the encoder is how it compiles all of this information together. And so that's a key element of this network. So each time you will look at the attention scores, compute the attention scores for each patch, then feed forward to the next layer. And you could just have many layers if you wanted to, as many as you wanted to. And then the decoder will then decode that into an output. And so in this case, we're doing classification. So it would include some attention layers to grab that relevant data in order to make an output. And just diving a little more into positional encoding, it's what happens when the transformer is going to give order to the data. So because transformers process all the inputs in parallel, you need to actually tell them which patches are coming first, second, third, and so on. So we're going to explicitly give them that information by numbering the patches like we did in that diagram that I showed. And there's something called multi-head attention, which is, again, what we are doing to focus on different parts of the input and compute attention independently, combining them to form the final output. Okay, so hopefully this gives a better sense of transformers and what is happening with transformers. And oh my goodness, I gave away my, I can't believe that. I gave away my answers here. Let's see, I guess let me fix that on the fly. A little bit of on the fly editing. Sorry, everybody. Take this down. Take down those darn answers to the problem. Okay. Here's for now. We'll show this. What is the purpose of positional encoding in transformers? Okay. Pretend like you didn't just see the answer. Remember, the transformer is computing all attentions simultaneously. Okay, remember that. So we do have someone say C. I'll just take that one first. It is actually very necessary to normalize your input data for a transformer. That's a very important step, but it will not be the answer. The answer would be B. So good job for that. Hopefully some of you were not able to see that before I showed it. But yes, so providing information about the sequence order. And then the other ones I didn't talk about. It does not speed up the training. It would not reduce the number of parameters, actually will increase the number of parameters because now we're encoding the position of every patch. So that's another variable to think about for the model to think about. Okay. Next, how does multi-head attention improve a transformer's performance? And I know we didn't talk as much about multi-head attention, but remember that multi-head attention is what's allowing us to eventually get an output by focusing on different things within the sentence or within the image. And so I have a couple answers here, mostly folks saying B or A. And I think we can maybe agree the answer would be A because, as we said, we're doing different parts of the input simultaneously. And Doodlegang says, will we be doing any exercises to practice or visualize these concepts? Yeah, so as soon as we're finished with this portion of the workshop, we're going to actually go ahead and try to implement Vision Transformer on our own. Okay. Yeah, exactly. I know I'm not doing very well with these quizzes. I would not be a very good test maker, I guess. Sorry about that, but yeah. So let's go ahead and now transition from NLP to computer vision. So we want to adapt the transformer architecture to handle images. We know that instead of processing entire images, VIT splits into smaller patches. The patches are flattened, embedded into higher dimensional space, and treated as input tokens to the transformer. And so we've talked a little bit about this, but just to reiterate, we're basically treating the image like a sentence, right? And let's talk about now the differences between CNNs and VITs, because a lot of you have probably heard the word CNN before, convolutional neural network. But actually, VIT is a very different structure. So CNNs, both of these process the spatial hierarchies in images. What that means is that they are going to extract the most important part of the image and use that to make a determination or an inference. But VITs are unique in treating images as sequences. So with the CNN, you'll use a filter to detect a local pattern. And basically, convolution stands for you're going to compute some kind of integral over the entire space to extract some filter. Has any of you heard about the dog and wolf example for vision learning? This is a really great one. Okay, not heard about it. So let me tell you about this example. This is actually an example of convolutional neural network, but I want to give you, it's more of an abstracted thing. But this is an example of a classification algorithm gone wrong. Okay, so you have a wolf and a husky. You're trying to get the different classifications between a wolf and a husky. And the CNN algorithm will build a filter to figure out where the important parts of the image are to get that difference. But look here at the filter that the algorithm creates. Isn't that funny? The algorithm looks at all the pixels that are not the face of the dog or the husky. It looks at the pixels around the dog to see whether there's snow in the background. And that way it knows that this is an image of a wolf or this is an image of a dog, a husky. All right. We all know, of course, this image is a husky, but the CNN will build this filter and use that to help it learn the classification difference. So always be careful when you are doing your classification. You never know what the algorithm is doing until you look deep into the code. And that's what we call interpretability of your algorithm. So make sure that you can check your algorithm and see what is it looking at. And for CNNs, this is how they do that. In ours, we're using VIT, so it's a little bit different. But just out of curiosity, does virtual reality games use VITs? I'm not sure if virtual realities games use those. If someone knows, please let us know. But I know that it's starting to become more and more popular in vision recognition programs because it is better than CNNs at certain performances. It's just a lot of computational power. And you'll see that when we get to our example, just how difficult it is to run. But yeah, you're right. Works on everything except for the main image, right? So you never know. But this is the idea of CNN. It gives you some filter. All right. So, maybe we can transfer back to this, actually. I hope I didn't mess up any other quizzes. But yeah, VITs excel in understanding complex visual scenes because they're not just using a filter like a CNN. They're processing the entire image as a sequence. And VITs work especially well when you have a huge number of images, even more, I would say, than CNNs. So if you have hundreds of thousands of images, this is going to be a great way to go. For example, let me just show you some paper results from the time of the publication of VIT. And H stands for the basically like the high complexity version of the algorithm, where you're going to have a lot of different patches. The more patches you have, by the way, the more complex the model gets to run, but the more accurate it becomes, which is, I guess, not super surprising. But definitely know that increasing the number of patches, it will increase your performance. So we have a bunch of benchmarks in this table, and the one we're going to use is CIFAR 10, which has 60,000 images. And you can see the improvement is very small, but it's real. There's about a 0.2% improvement. But then look at the CIFAR 100, which is an even larger data set. And you see there's a full 1% difference between the VIT and the state-of-the-art at the time back in 2020. Okay, so this is a really solid algorithm. All right, so this is a good question. It's possible that they use this model. I'm not sure. I don't have any insights into where this is being used commercially, unfortunately. Although I do think that so a lot of the self-driving technology uses CNNs, but I think there's some efforts to make those towards transformers. But that's just anecdotal. All right, so we're on to our next quiz, vision transformers versus CNNs. I want you all to think about this. How do vision transformers process images differently from CNNs? Okay, think about this a little bit. We learned about VIT. You might know something about CNNs, or just even using what we talked about today. VIT, so using convolutional layers is actually what the CNN does. So it's not A. And then B would be directly analyzing pixel values, but actually vision transformers will patch those into sequences. And that gets to part C, which is treating images as sequences of patches. So that's right. And then pooling layers will be implemented in both cases because both situations require an inference to be made. So in the case of vision transformers, we want to do a classification, object detection, whatever it might be. And same with CNN. So we're going to reduce those dimensions of the highly complex image data. All right. And then here's another one. I guess I gave away the answer already, but let's just go through this. I'm kind of embarrassed about this. I thought I fixed all this, but I guess not. But let's just go through this one. Abhinav says D. Yeah, good job. Yeah, so the one advantage over the CNNs, it's not that they require less data to train. They actually require more data to train, I would say. They do not have fewer parameters. They are probably similar difficulty to implement, but if you're doing it from scratch, I would say VIT is probably even harder. But then they capture long-range dependencies more effectively. So that is part of the VIT framework because you're going to encode all of the position information of the image and then process it simultaneously. So if there is some strange relationship between the top right corner of the image and the bottom left, you're going to get that with VIT. And with CNNs, it might not be represented in that same way. And Doodle asks, what's the definition of CNN? It is convolutional neural network. Sorry, I didn't define that super well, but it's not, yeah, that's not going to be super relevant for the rest of the workshop. So don't worry about that. Okay. Oh, great. I'm glad I'm the first teacher to get your name right. Awesome. So now let's practice a little bit. And this is what Doodle Games was asking about. When are we going to get some practicing going? Yeah, exactly. The same amount of data amount will work good. I would say it depends. So if you have a small amount of data, probably CNN will work better because it's a reduced complexity model. Now, if you have a large amount of data, VIT will probably outperform that CNN algorithm. And honestly speaking, there are probably more performance for VIT at a broad range of data than CNN. So I would say objectively, VIT probably outperforms CNN at most cases. But performance is not always the best thing. Let's go back to this diagram here. Look at the difference here between VIT and some state-of-the-art models. You can see that VIT is going to be maybe a 1% increase on some of these data sets, sometimes even less. So what that indicates is that, yes, if you need an extra 1% accuracy, use VIT, but is it really worth the extra computational cost? Hard to say. It might cost you a lot of money to train a VIT when you could easily use a CNN and get everything you need. So definitely look into that before you start training. So, okay, let's practice then. For today, we're going to use a product called Google Colab, and the link is over here. So let's go ahead and go to that link. I'm going to fix these quizzes so that if we do this again, let me just fix quiz number 3. I'm so surprised that, all right, quiz number 3 is fixed. So let me send the Google Colab link here. And you should be able to create a new notebook. I'm going to create a new notebook, certainly, so that we can do this together. If you're not signed into Google, of course, it will not work. And you don't need to subscribe to Google Colab, but personally, I've been subscribing to them for a couple months because you can choose to get access on demand to their high-performance computer. So you get kind of some priority there. But with a free version, you can almost always get a really solid computing resource, and you're going to want to change the runtime type. So regardless, so go up to this top right-hand corner and click on change runtime type. Okay, and I think you should be able to see everything I can see here. You can ask for any of these GPUs. I think you cannot use a TPU because TPU would be would not work with certain things. But try it and let me know if the TPU works for you for this use case. But yeah, maybe I'm just going to use this normal A100 and clicks. And runtime of Python is totally good. Do you have T4 GPU? Doodle Games? Maybe we could try with T4 GPU because that will be available for everybody. And then just click Save. Okay. So let's go back to our slides a little bit here while we wait for everyone to get connected. Try to get that T4. Oh, and you also have V2. Interesting. I wonder what V2 is. Oh, TPU V2. Okay. Yeah, I think we cannot use a TPU because it's a different architecture. But I'm not sure. It might work. We'll see. But anyway, so we're going to use Google Colab. Everybody try and get to that page. If you're unable to, that's fine. We'll get you there. But just send a chat, and then that will really help. But you're going to want to install the necessary libraries. So we're going to do a pip command into the notebook. Pip install Torch, Torch Vision, TIMM, and Matplotlib. Okay. So let me do that on here. We can do pip install Torch, Torch Vision. Torch is a really good open source machine learning library that a lot of stuff is built on. So that's why we're installing it. Tim is going to be a model repository type thing. So there's a lot of models that you can load from Tim. And then Matplotlib. I'm not sure if this part is necessary, but we are going to be plotting. So I just figured why not just keep that in there. And when you click run, it should begin to install. And yeah, just to let that run. And so while this is running, I'm going to answer a question from the chat by Wait Walker. At the end of this course week, what can we make that is real world applicable? And I'll say it's complicated because it depends on what you mean by real world applicable. These models are designed to give you tools in your toolbox, and then it's up to you to create things with them. So right now we're giving you a tool called Vision Transformer. And if you have a image data set, you need to do some object detection, image classification, go on and build those things, right? Try to enter a hackathon and use these tools you're learning to build something. That's how things click. And actually, at the end of this workshop, at the end of this particular stream, we're going to give some time for you to actually go on your own. So I want you all to go on your own and improve on this algorithm, improve on our code that we build today, so that you can try and get some practice with that. Okay. So yes, I think Matplotlib is probably installed by default, but anyway, let's go through. It looks like everything did install okay. And we can actually do another code. And if you go back to the slides, the next step is to import Python modules. So, this is a lot to type out. If you don't want to type it out, I don't blame you. But I'll be typing it out. And if you want to just copy straight from the slides are there for you. So go ahead and copy it out. But yeah, let me just import all of these modules. And while I'm typing this, I'll tell you what some of these modules we're going to use them for. So specifically, the NN module is great because you can get some super simple architectures and layers, especially layers for your algorithms. So we're going to use a simple linear layer, and that's going to come from the NN module. And then transforms, I believe, is used mostly to transform inputs and outputs between layers. This next one we're going to use is for data sets. So we're going to get the SciFAR 10 data set from Torch Vision itself. So that's great because it means we don't have to we don't have to download it onto our local machine and then upload it to Colab. That would be a headache. And the Optim module is good for the optimizers, which are used for training the model. Data loader will easily load in those images in a way that the model can handle and process. This random split function is going to split our data set, our SciFAR data set, at a random for random selections between training and test data sets. So we're going to use training data sets to train the model and make sure that it's improving every time we run it. But then we're going to use test to make sure that the model's not getting overfit, meaning that it's not getting so specifically used to the training data set that it forgets how to look at new data. And then finally, we have our TIM, some date time information, and some plot functionality. I'm not sure if this is necessary actually, but sometimes that's useful for putting in training times and things like that, telling you wall clock times for your training. Oh. Thanks for explaining that. When I run this, it works for me, but I did see someone said I got an error. I hope I didn't write time That's a good point, though, Jupiter shoulders. So always watch those typos. Yeah, so, okay, some peoples are running successfully, so I think we're going to move on to the SciFAR dataset. This is widely used for training ML models. You saw even in the paper that we looked at for 2020, they use SciFAR 10 as a benchmark. So it contains images with 32 by 32 pixels, okay? Really low resolution data. Actually, maybe I can find an example to show you all of what a SciFAR image looks like. It's not something that you would see like in your normal like iPhone photo. It's kind of funny. I'll send a link too if anyone wants to check it out. And I'll link the slides again, just so everyone has that. But yeah, this is the SciFAR 10 data set. So it's really low resolution. Honestly, I have kind of some trouble figuring out what these things are. Like, what is that thing, you know? What is that thing? But it's simple because there's only 10 classes. So these are airplanes, automobiles, birds, cats. And we just want the model to tell us which of the 10 categories does it fit in. Look at this one. What the heck? I don't want to make fun of anybody's dog, but look at this dog. I would have an extremely difficult time telling you what that is. All right, anyway, that's enough about SciFAR 10. We're gonna try and now actually load that, okay? So let's load that in. Here's the code. Again, if you want to copy that through, go ahead. But I'm gonna type it out as I mentioned, just like last time. So let me get my share screen going. And we're going to do transform equals transforms.compose. Oops. The darn autocomplete sometimes bugs me. Maybe I'll just use some of this autocomplete stuff if it does match. Yeah, it knows actually that I've written this before in a previous notebook. But yeah, so let's just take a look at these. We're going to resize the image to 224 by 224. The reason is we want to match the resolution of the model which we're going to load. So the model we're going to load is 224 by 224. So we're just blowing up the images. Then transforms.toTensor will convert this to a tensor, which will contain the information and then a data type that is very good for the model, and normalize that. So this is normalizing each value on some mean and standard deviation. So we just subtract the mean, divide by standard deviation to get some nice normalized inputs. Somebody asked about inputs earlier being normalized, being part of VIT, so that's definitely part of it. Tensor is just a high dimensional matrix. Yeah, so we could encode X, Y, red, blue, green colors. That would be example of a tensor. You're not just encoding 2 dimensions. All right, so next we want to get our data set actually going. So we have data set equals datasets dot SciFAR 10. I'll let it do some autocomplete, but actually I think this autocomplete is not quite right. So we're gonna download that into our root directory, have some train size that will be 80% of the data, and then some validation that will be the rest. And then we will ask random split to split the data set according to these 2 sizes. All right, so look, it's downloading all this data. This is a much better explanation than mine, but yes, so basically you would use tensor to mean some high dimensional object of data. I did not know that scalars would be tensors and so would vectors. So thanks for giving that information. Yes, it's used a lot in physics. So for example, quantum mechanics, general relativity, optics, you use tensors. So, all right, let's go ahead and move on now to the next bit, which is our data loader. So we have a loader, train data set. Batch size means how many images will we give at any given time. Wow, sometimes the autocomplete is really not my friend. And number of workers. So we just load those in. And we're on to our next portion. So we're going to talk a little bit about data processing and data augmentation. We might not implement a lot of this, but we are going to implement some. So just to let you know that augmentation increases the diversity of the training data set. So think about this. If I have a water bottle, let me take a really simple Gatorade bottle I have here. This bottle, if I give the computer pictures that look like this, 1,000 pictures like this, it might not recognize a water bottle that looks like this. All right, so by rotating the image, we might artificially give it more examples to learn from. So does the rank, oh, someone says, could you please quickly talk through this code again? Yes, so basically, first step is building the transform function, because remember, we can't just raw put in images into the model. We have to resize them so that they match by blowing them up, put them as a tensor object, and then normalize, which lets us put all the values in a strict range that machine learning algorithms really love. So then we will load in our data set, our CIFAR 10. You can load in another data set if you want. There's tons to choose from. And if you want to try another one, that's actually one of the future exercises. Then we split it into train and test data sets using random split. And finally, we use data loader to load that through. Okay, so hopefully that helps, but definitely give a question if you have one. But now we're going to actually talk a little bit about adding some kind of training augmentation. So we're going to add to the transform train a little extra code, which will basically give us horizontal flips and some random rotations to throw in there. And hopefully that will help us to augment our data set so that we have even more. Okay, so not going to rewrite all of that. Instead, I'll just leave that up there for you to check. It should be, possible to implement that. I'm going to actually leave that as a possible exercise for you to try. But just remember, it's on the slides if you want to do that. But I'm going to move to a quiz. We're not going to implement any augmentations right now, but let's just quickly go through a quiz. What is the purpose of data augmentation? Does anybody know based on our conversation? All right. Someone says I play a sci-fi character. So cool. Awesome. Yeah. So a lot of people are saying D, and that would be the case. So we're going to not necessarily add more data, but if we're restricted in what we have, we can do things like random rotation, flip. I'm going to leave that as an exercise for you all to try so that you can maybe improve the score of our data set. And here's another one I want to talk about. This is based on the code that I showed you. So what would be some common data augmentation technique for images? Can you think of one based on the code we looked at? All right, a couple answers here, but mostly people are saying A, and that's correct. So random cropping would be. Actually, this is kind of a bad question because none of these are ones that I implemented, but yeah, maybe ones that we did look at in the code base were rotation or flipping. All right, so now we're going to load and fine-tune a vision transformer. So we're going to create a new class called VIT model. Okay. And am I showing? Yeah, I am. So we're defining a new class called VIT model. Since this is not actually commonly implemented in a lot of cases, at least not as commonly as, say, a CNN. We're going to have an init function. So when we build a new VIT model, this will run, and we will use the super to inherit all the properties of VIT model. And then we will just use this. Oh, I have a nice little fill in here from my previous codes, but self.model to say that we have a new model that will preload in from Tim. So look at this. This is a preloaded one. It is a patch 16. So that means it will have 16 different patches and 224, which is the number of pixels that it requires. So it will just break into 16 patches, 224. You could probably upgrade this to 32. I'm not sure if that's a model, but that would be improved accuracy. And then here we have a model head, which is just a linear layer that will connect our model. And so now we can just say some feed forward function. So when we call this forward function, it will update the state of the model. All right. And let's give a few hyperparameters that we should talk about. We are currently on slide 37. So just to give you an idea of that, we did not implement this code. Oh, on slide 35. Good question. We did not implement this code. I'm going to leave that for you all to try on your own, because at the second half of this workshop, I'm going to give an exercise to actually see, can you improve this model performance? But now we're going to add some hyperparameters. So these are what we call hyperparameters. So batch size, for example, LR stands for learning rate. So we can make the learning rate high, which will converge the model very fast, make it just freeze up its neurons very quickly. Or we can add that to very low learning rate, which would make the model think a little bit more before it converges. And then number of epochs, number of classes we will not change, but number of epochs would be time of training. So we could train for a very long time, actually, and see if that improves the score. But these are our hyperparameters. So let's go into our model and into our code. And we're going to put these in there. I'm just going to copy them in. And we'll just run that to get some idea. Okay. So next we're going to implement the training loop. And it's too much code. I'm not going to show it here. But I am going to paste it into the tutorial. Actually, maybe I'll just transition to the solution now. because it's getting to be a lot to type everything. But once we have our VIT model, the next step is to initialize the model and the optimizer. So first, this line of code here chooses a device. So if you have set your GPU to T4 or some other one, if you have a subscription to Google Colab, then that will bring you to CUDA, which will run your model a lot faster. Otherwise, it'll use a CPU, which might actually take you an hour or more to actually train this model. The GPU that I used took me maybe a few minutes to get through the 10 epoch training cycle, but yours might take hours if you use CPU. So try to use that T4 first. Then we initialize the model, a new instance of the VIT model class, and we're going to give a parameter, number of classes, 10. Remember, when we did find our model, we asked it to give some, how many modules will you want for that? So that's important. So then we will have some criterion that we will judge our model on. Cross entropy loss is the most common classification criteria. And it just shows, again, how well are you matching up the real result with the prediction. And finally, the optimizer. So the optimizer will tweak the parameters of the model according to the learning rate. And we set that learning rate earlier as a hyperparameter. And then we have our training validation loop. So some train loss, validation accuracies. We'll store all of that information. Remember, Abhinav, you said an error there. It's showing no module named Tim. Remember the first slide that we did for code? We had to actually install that. So go to slide 30, and I'll paste the command as well in the chat. And then remember, after that, you have to import Tim. So try both of those. But yeah, so we will use a really simple training loop. This is something that you will see in just about every single machine learning application. But basically, you are going to optimize for one step, calculate how well the model's doing, adjust the parameters, keep going, and it will print out what's happening. Save the model and plot. So yeah, you're welcome to run the code, Doodle Games, if you would like. Feel free to. We have a pre-trained model here because it does take quite a while. And I wanted to show you an example of how it looks. So loss is basically how poorly is the model doing. The higher the loss, the worse the model is doing. And you can see accuracy is also plotted. So as loss goes down, accuracy actually goes up. And you can see we're hitting validation accuracies, which means how well did the model do on the validation, that 20% of the data which we don't use to train. We're hitting validations of 95%. And as the training converges, which means this loss is getting lower, but it's not getting much lower over time, we get to the final result of the model, which is here. So this is the best possible validation loss. And you can see the accuracy stabilizes of our model around just below 95%, I would say. And if we keep training for more and more epochs, it will keep converging towards this final number, which is probably around 95%. Okay, so what that means is that every time it sees a CIFAR 10 image, even that crazy dog we saw, 95% of the time it will get that right. And only 5% will it mismatch them. If you recall from our previous example of the CIFAR data set, there was actually a 99% accuracy for the Google version. So that brings me to my next thing. Let's talk about a quiz here. What's the purpose of fine-tuning a pre-trained model like the one we did? Some people saying C. Yes, to adapt the model to a new task by training it on a new data set. So we took a preloaded model from the TIM world, and we just used it to train on CIFAR. And what hyperparameter controls the rate at which the model updates its weights? Do you remember? We talked about it very briefly when we were doing the hyperparameters. I'll give you a hint. It's not batch size. Yeah, it's C. Excellent work. It's learning rate. How fast will the model converge? If you go back to that plot where the model's going like this, that's the steepness of this curve. And so just giving you some term definitions from what we saw, accuracy is the ratio of the correctly predicted instances to total instances, and that's what we were measuring. There's a few other things like precision or recall that people might use, but accuracy is what we were using just now. And just giving you some ideas on confusion matrix, this is the predicted versus actual state of the model. So 98% accuracy means that, or 95% accuracy means that 95% of the values were in these green shaded boxes, and only 5 were in those red shaded boxes. All right, so again, these are the codes to visualize model performance. We kind of already talked about that, but I want to now turn to the challenge portion, okay? We did today transfer learning with vision transformers, but there's many other things you could do and applications. And I wanted to actually give you some challenge. So first of all, here's the challenge. We will ask you to explore the VIT concept on your own. All right, I want you to try to get a score higher than 95% on CIFAR 10. So remember the workshop code, make your own revisions, see the next slide for some ideas, and post your score to the Discord and explain your code changes. All right, so I want you all to try this in between this workshop and the next one. And I will give you a shout out on Discord if you're able to get 95% or higher, okay? So ask me any questions you have along the way. And yeah, I'm just trying this as kind of a new idea with this workshop to see if you all are interested in actually doing some interactive stuff on your own. So try these ideas. I actually gave you some starting points. So the first one was modify vision transformer, play with the hyperparameters. There's another idea, which I didn't put here, which I'll put on the slide, which is data augmentation. So try that too. See if any of that works. A good question from Doodle Games. So the score is actually right here. So if your model can hit above 95%, I guess this model is kind of breaching 95%, but I really want to see it get more like 90, push to almost 96% maybe at the end. That would be awesome. So just use this plot as a way to check whether you're doing good or not. All right, so the ideas are in the slides. I'm going to give the slides one last time here, and hopefully you all can try these out and let me know if you run into trouble, if you think of a new idea. Remember, posting those in Discord is a great way for our community to improve. But yeah, so just to give you some other slides here, I put a link to the original Vision Transformer paper if you're interested in learning more of the math behind it. Image is worth 16 by 16 words. Super, super popular paper, and I highly recommend looking at it. And yeah, I put a little bit of other ideas of some other things. So yeah, that's everything I have for today, but I'm glad you all appreciate the slides and the lecture. And I will be monitoring the Discord until the next workshop. So just post to me and I'll write back to you. Workshop code is in the slides, Rampant Rajesh. So check out that. Glad you all enjoyed. If anyone's not in the Discord already, I'm going to send an invite link. Next workshop should be in about 1 hour. So just see where you can get in 1 hour. I always think it's good to do that. If you don't want to do the challenge, I can't make you do it. I can't force you to. But I'm just offering that for another hour. I'll be in the general chat, community support, wherever you want to, off-topic channel. So just ping me as Stephen from MLH. Oh, that's not right. I meant to copy my username. I forget how to do that sometimes in Discord. Okay, so yes, the LCPU code should work. If it's saying you used all available RAM, what you can do is try to request higher RAM. You could try to do some free trial of Colab. Sometimes they'll give you a free trial, and you could use that. There might be some another one that you could try. So there's this thing called, I think it's called Paperclip. Is that what it is? Paperspace. Try another thing like Paperspace. But yeah, it's kind of a hunky model. I don't know if that's a good word to describe it, but it's a big bear of a model. So yeah. What happens in Tetris mini event? It's awesome. I highly recommend doing the Tetris mini event. Yeah, basically it's a competition. So you can get really good at Tetris if you go to all those. I hosted the Tetris mini events for a really long time for Global Hack Week, for many, many sessions. And yeah, I got really good at Tetris. So you will too. Yeah, but thank you for the kind words. They were Graymons. And yeah, just try to do some research on that before and then play some Tetris. Why not, right? All right, if you've used up all your RAM, you can end a session. Free trial only lets you run one Colab at a time. Okay, yeah, you might have more than one Colab open. There could be a bunch of different things. But yeah, let me know if you have trouble while you're working through this. And yeah, I'll see you all next time. No problem. All right, take care, everybody.